The only thing we have on the agenda today is review for exam 7 in chapter 9. And I'll be working from the version 2 review document. I believe that's the one I handed out. Okay, let's see. We've had a lot of excitement here in the past few days. I hope everybody's been getting email or text notifications from the school about our ransomware attack. And just yesterday afternoon, they finally released the system so we could get back into our courses. So has anybody not tried to access the course, or tried to and failed? Because if you have trouble, you need to contact the help desk and let them iron the problem out, because maybe they missed somebody, right? Getting you all everything fixed back up the way it should be. Otherwise, we'll assume that everything's running normal, and we're going to look at some highlighted problems here. Number 1, let's see. I guess I'm going to have to scroll this one. Either that or shrink it. Maybe I will. I'll shrink it. Let's go down to 200 and see how much that gets in. No, not quite. About 185. Almost. 175. There we go. Which of the following molecules contains a central atom with sp2 hybridization? All right, so we're looking for sp2 hybridization. Remember what sp2 stands for. When you know that something is sp2, what is its electronic geometry? All right, 2 here, 1 there, that's 3. That means 3 groups, either bonded or lone pair, and that would be trigonal planar. That's electronic. So what we could do is, when we look at these different molecules, we might see the possibility for an actual bent geometry. But if there's a lone pair also in there, that's trigonal planar, which means it's sp2. So let's look at each one. I'm not going to write them all up here. The first one, when they talk about central atoms, that is, if it's a simple molecule where you only have one possibility for a central atom, that's easy. But if you have multiple locations for geometry, as in the first one, you have the possibility of a geometry around aluminum, and you have possibility around phosphorus. Those are considered central atoms. Well, we notice that aluminum, the way it's written in this Lewis structure, has 4 groups. Right? That's sp3 hybridization. Phosphorus also has 4 groups, sp3 hybridization. So A can't be it. How about B? Right? In the case of B, let's see, who is that? Oh, I should have scrolled down. I missed a few. Hold on a second. Let me get everybody recorded here. Let's see, the last one. This is Amber. Zoom. Okay. Heather. Zoom. And Brittany. Zoom.
I finally made it too. I was a little late.
Kathy. Okay. Well, I was late picking up on things too. While I got you here, let me digress for just a moment. Let's see, I need just 1 second here. Brittany and Tina. This message is for Brittany and Tina. I don't know what happened. I marked down having received your lab report for, let's see, for, well, where is it now? Molecular weight of an acid by titration. I know you gave it to me because I marked it in my book, but I cannot find your hard copy. If you have an electronic version, that's fine. Just submit it in Brightspace for me, if you would. Or if you don't, well, you should have, right? If you did it in a word processor, you should have it available. So I'd appreciate it if you, Brittany, and Tina would submit your copy through Brightspace, and then I'll be sure not to lose it. All right, so let's get back to where were we? B. Okay, in this case, we see that and you have to assume that each one of these Lewis structures is correctly written. Right? B has 3 groups around it. That's sp2 hybridization, right? So that works. B works. C has 4 groups around it. It has 3 hydrogens and 1 lone pair, so it's sp3 hybridized. This N2H4 molecule, which is hydrazine, has around each of the nitrogens, you have 4 groups, sp3, right? So B is correct, C is not, D is not. And how about E? Beryllium dichloride. It only has 2 groups around the beryllium. So it would have to be sp hybridized, right? So it can't be. So B has to be the answer. Right? I took a lot of time to work on that one, but if you don't have the Lewis structure drawn and the same question appears, you've got to draw the Lewis structure in order to answer the question. And all you need to know is how many groups are around that central atom, and that will tell you the hybridization. All right, number 3. Okay, consider the molecule and the following hybridization choices. What's the hybridization of the carbon atom that is double bonded to oxygen? All right. This is an organic molecule. And let me go ahead and draw it out. Let's see. 4 carbons. Then a triple bond to a nitrogen. Yep. And then a chlorine and a hydrogen. And then a double bond to an oxygen. And wait a minute, I've got, let's see. 1, 2, 3, 4. That's right. Oh, sorry. Wrong place. That one. And this one has the chlorine and the hydrogen. Right, 1, 2, 3. And each one of these is also a hydrogen. Okay. What's not given to you there is any possibility of lone pairs. Okay. So we have to be sure that what we've drawn is a correct structure. There's a rule of thumb that I haven't given you yet. It comes from organic chemistry. Carbons tend to be bonded to 4, maximum of 4 bonds. They don't always have 4 bonds, but a maximum of 4. So this one is complete. In fact, you can say 2, 4, 6, 8. That's an octet. We know that. 2, 4, 6, 8. That's an octet. 2, 4, 6, 8. That's an octet. 2, 4, 6, 8. That's an octet. How about nitrogen? 2, 4, 6. Nitrogen has a lone pair right here. Oxygen has 2, 4, 6, 8. So there are your lone pairs. But actually, that's superfluous to answering the question, because the question is, what's the hybridization around the carbon atom that's attached to the double bonded oxygen? That's this one right here. Well, we know we have 1, 2, 3 groups, which is sp2. That would be B. Okay, for number 5, we want to draw that structure. And in this case, the lone pairs will be important, or could possibly be important, because we want to identify the hybridization around each one of the carbon atoms. We've got 5 carbons here. Number 5 has 5 carbons. 1, 2, 3, 4, 5. See, this one has, and when we write organic compounds, whenever we have a string of carbons, see, we could write this like CH2 and then C H and then CO. And when we do it that way, we understand that those hydrogens are attached to the carbon, and this carbon is attached to that carbon. But fortunately, the way this is written, and I think we did it this way because you don't know the language of organic chemistry. These hydrogens were put out here so that it would be shown that this carbon is bound to that carbon. And in fact, it's a double bond. But when we stick that hydrogen in there, that hydrogen is bonded to the carbon, not bonded to this carbon, not to that carbon. Then we have a double bonded oxygen, and we have 2 hydrogens here. Then we have a triple bonded nitrogen. And of course, we have a lone pair on that side. Now, that carbon's got an octet. This one's got an octet. 2, 4, 6, 8. That one's an octet. 2, 4, 6, 8. That one's an octet. And if we put these hydrogens out here, 2, 4, 6, 8. So we have lone pairs there, of course. Now this is this is number 1, 2, 3, 4, and 5. These are just numbered for the carbons. Now, what's the hybridization here? Well, now that we have the structure written correctly, we can say 1, 2, 3 groups, sp2. 1, 2, 3 groups, sp2. 1, 2, 3 groups, sp2. 4 groups, sp3. And 2 groups, sp. Right, for the carbons. So let's see. If we go in here and we're trying to go quickly, we say sp on the end. Carbon 5, that's either A or E. And then we back up 1, sp3 has to be A. And you can check the others. They're correct. So A is the answer to number 5. All righty. Number 6. Hybridization of selenium and SEF6. In this case, we do have to write the Lewis structure. So where is selenium located? Well, selenium is in the same group as oxygen and sulfur. Right? So how many valence electrons does it have? Count over from the left, and it has 6. So 6 electrons here. This one is 6 times 7, because fluorine is a halogen. So that's 42 plus 6 equals 48. Okay. 48 electrons. So we put selenium in the middle, and we put 1, 2, 3, 4, 5, 6 fluorines. Okay. 2, 4, 6, 8, 10, 12. 36 electrons left. All right, if we put 2, 4, 6 electrons around each one of those fluorines out of this group, then we'll have 6 times 6 is 36. We used them all up. Okay. Okay, so now we've accounted for all of our electrons, and we have 6 groups around the selenium. So how is selenium hybridized to give you 6? Well, we have sp3 would give us 4 of those, and we need 2 more. We need 2 Ds to do it, to give us the 6. 2, 3, 4, 5, 6. D2sp3, which is E. Now, just to remind you, why can we do that for selenium? Because selenium is in period 4, right? Period 4, actually period 3 and larger has access to d orbitals. Period 2 does not. And period 1 definitely does. And period 1 doesn't even have access to p orbitals. Period 2 has access to p orbitals. Period 3 and greater has access to d orbitals. So that's where we get the extra 2 Ds that are allowed for selenium. Okay, I did say that was, yeah, E. E for number 6. All righty. How about number 9? A pi bond is the result of, well, we're going to have to take these one at a time, I think. Overlap of 2 s orbitals. If you overlap 2 s orbitals, you can only get a sigma bond because they're spherical, right? And the 2 atoms, whatever nucleus is in the center, it has these s orbitals here and here. They can only overlap that way, right? You can only get a sigma bond out of s orbitals. So A can't be it. Right? A's B out. How about B? Overlap of an s orbital and a p orbital. The only way that can happen is also a sigma, because the s orbital is spherical and it can overlap a p orbital. That's possible, right? For instance, hydrogen. If we overlap a hydrogen with, I don't know, I'll paint myself into a corner. Hydrogen only has s orbitals, and it can overlap with a p orbital like that, but it has to be in line with the nucleus. So that's a sigma bond. You can't get a pi bond out of that. Right? C, overlap of 2 p orbitals along their axis. If you do that, that by definition is a sigma bond. If it's on their axis, it has to be a sigma bond. But remember, you don't get pi bonds until you've got at least 1 sigma bond. So how does it do that? Sideways overlap of 2 parallel p orbitals. That's the way you do it. And E is just stupid. Sideways overlap of 2 s orbitals, it's not going to happen. The only way s orbitals can overlap is on axis to give you sigma bond. So D is the correct answer here. All right. D is the correct answer because you get a nucleus here and a nucleus here, and you have unused p orbitals here and here, and they overlap off axis. That's how you get a pi bond. So the answer to this one is D. All right. Number 10. All right, we've got these 3 structures, and I think I showed you these in class. In organic chemistry, when we draw a structure, we leave out the carbon atoms, and we leave out the hydrogen atoms too. So if we draw, let's see, 1, 2, and 3, we draw this 6 carbon ring. Each one of these is a carbon, right? All the way around. And you got that for each one. Okay, but in the first one, you have, let's see, they put the double bond here, here, and here. Well, remember, carbon can have 4 bonds maximum. So if we don't draw anything in here, we're saying that, right, 1, 2, 3, 4. The 4th bond is occupied by hydrogens. And that's why it's written as C6H6. All right, for the second one, we have a double bond here and here. So that means we have hydrogens there, there, and there. And for these, we have 2 hydrogens. That's why this one is written C6H8. Okay, and then the last one only has 1 double bond there. So we have a hydrogen here, here, we have 2 there, 2 there, 2 there, and 2 there. This is C6H10. Okay, now to the question. Which molecules have p orbitals that share an electron pair to create pi bonding? Well, anytime you got a double bond, you have pi bonds. So each one of them has pi bonding. Right here, here, and here. All of them do. All of the above have electron pair sharing in p orbitals that creates a pi bond. Now this one has 3 of them. This one has 2. This one has 1, as written. Right? We know that when you get to this place, what you get is a special delocalization of electron density in this region above and below the plane of the molecule that gives you a special stability. It's called an aromatic structure. Okay, use the molecules below to answer the next question. Which molecules have equivalent carbon-carbon bonds throughout the molecule? All right. So number 11 then looks at each one of these molecules and says, all right, which one has equivalent carbon-carbon bonds through the entire molecule? Well, when you only have 1 double here, this one is going to be a short bond. And these are each going to be similar. Right? So that we've got 1 here that's out of place. In fact, it puts stress on the ring. It shortens and strengthens that bond, but the others are single bonds. Right? So they're further apart, and that stresses the ring. This one has a certain these right here, right? Because they're what we call conjugated. We have a double, single, double. Whenever you have a double, single, double in a carbon chain or a ring, you get the delocalization of electron density in that region. And that makes these 3 equal, and these 3 are equal. These 3 are equal to each other. These 3 are equal to each other. Right? But you don't have the same bond equivalent. You don't have an equivalent bond for the entire molecule. Now, when you get to this one, you have double, single, double, single, double, single, double, single, double, single, all the way around. That means that every bond in this molecule is exactly the same. And it's been proven. I mean, it can be measured. The bond strength, the bond length, the structure of the molecule, all tells us, all that information tells us that every carbon-carbon bond in this molecule is exactly same as the others. Right? So A is the only one that has equivalent carbon-carbon bonds through the entire molecule. All right. Okay, let's go to 12. All right. Scroll up a little bit and get 12 and 13. All right. sure I'm still centered. There we go. The electron configuration of a particular diatomic species is, right, what's the bond order for this species? Okay. If you remember the shorthand version here, what we have is bonding and anti-bonding orbitals. The anti-bondings have the asterisk, right? So this first one is built from the 2s, and it has 2 electrons in it. The second one is built from the anti-bonding. It has 2 electrons in it, and it's also built from the 2s, and so forth and so on. Right? So that tells us which electrons are bonding and which are anti-bonding. So in order to calculate the bond order, it's simply a matter of saying how many are bonding. And we look at them, we count them, right? Look for the bonding ones. There's 2. There's 2 more, 4. 4 and 4 is 8. So we have 8 bonding electrons. And then we look at the anti-bonding orbitals. There's 2, and 2 is 4. Right? Minus 4, then divided by 2. So that's 4 divided by 2 is 2. So the bond order for this particular diatomic species is 2. D is the answer. All right, 13. As the bond order of a bond increases, the bond energy increases or decreases, and the bond length increases or decreases. So we got to fill in those 2 blanks. As the bond order increases, right? Bond order increases. What happens to the bond energy? The bond energy also goes up, right? It's a stronger bond. And bond energy means how much energy do you have to put into the bond to break it? And the bond length, though, with stronger bonds, the bond length decreases. So the bond length decreases. It gets shorter. All right, so that would be C, increase, decrease. All right. Okay, number 15. How many unpaired electrons in the F2 2+ ion are based on molecular orbital theory? The order of the molecules orbitals are. Okay, so just to keep things simple and focused on one question, you're actually given the energy order of the molecular orbitals. Right, so we're given, let's see, sigma 2s, sigma star 2s, and then we get sigma 2p and pi 2p, sigma 2p and pi 2p. Then we get pi star, yes, we get pi star 2p, and we get sigma star 2p. Okay. Now, how about the F2 2+ ion? Okay. F2 2+. All right. How many electrons would there be if it were neutral? All right. If we only had that molecule. Well, we're only looking at the valence shell. Right. Fluorine is in the second period. We're not even considering the 1s shell. It would be out here somewhere. So in order to use this arrangement, we just need to count up valence electrons. Right? For 2 fluorines, that would be 2 times 7 equals 14. For the neutral atom. But notice it's a 2+ charge. That means that we've lost 2 of these, right, to give us a 2+ charge. So 12 electrons are what we have to put in here. Now, how many electrons can go into a sigma orbital? Only 2. So we have 2, 4, 6. We have 6 electrons left, right? How many can go into the pi? Well, 4 actually, but we have 2 levels here. Right? We have 2 levels there, 2 levels there, 1 level there. So here, 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 right? It'd be like that, maybe like that, like that. Then we have 6 electrons. We have 1, 2, 3, 4. Right? 2 electrons left over. Okay, where do they go? We have to obey Hund's rule for the molecular orbitals as well as we did for the atomic orbital. So we would have 2 electrons, 1 would go to here, 1 would go there. And so we have 2 electrons in there. And how many unpaired electrons are there in this molecule? 2 unpaired electrons. How many unpaired electrons? Not how many pairs, but how many electrons? 2 unpaired electrons. That's C. Okay? That's how we do that one. Now, if this stuff still looks foreign to you, that's probably because you haven't done enough of them. Gets easier with practice. The hybridization of the central atom in ClF2 plus. Hybridization of the central atom in ClF2 plus. ClF2. 1 plus? Yes, 1 plus. Okay. So this one, we just go back to the valence bond theory and take 7 here. 2 times 7 is 14 there. So that would be 21 minus 1. 20 electrons. Right? That's how you get the plus charge. You drop 1 electron. So if we put chlorine in the middle, fluorine on the ends, that's 2, 4, 16. 2, 4, 6, 8, 10, 12. That's 4 electrons. Okay, so 2, 4. So the hybridization around that central atom is 1, 2, 3, 4 groups, sp3. Okay? All right, number 21. Which of the following does not contain at least 1 pi bond? Okay, so let's take A, B, C, D, E. E is none of the above. Okay. All right, so we got H2CO, which is formic acid. Yeah, that's formic acid. I think. H2CO. No, that's formaldehyde. This is formaldehyde. Right? Anybody who's had a biology class where you dissect a preserved specimen knows what formaldehyde smells like. CO2 and C2H4, C2H4 and C2H6, C2H6. Okay. We've done carbon dioxide before. Right? So we're looking for the one that does not contain a pi bond. It says at least 1. That means it doesn't contain any. Does not contain, right? Be sure and read that. Not contain a pi bond. And this one, like that. Right, so carbon dioxide's out. What about formaldehyde? Well, we'll go the full route. Right? That's 2 electrons, 4 electrons, and 6 electrons. Right, so that's 12 electrons. So we put carbon in the middle, oxygen, hydrogen, and hydrogen. And there, so that's 6. 6 electrons left. So we put 2, 4, 6. Okay? Used up all of them. Carbon needs an octet. So we take those 2, make a double bond out of it. Okay. So this one has a double bond. It does not answer the question. How about C2H4, right? So we have 2 carbons, which would be 8 electrons, plus 4 is 12 electrons. And so we put a carbon and a carbon. The way that's written, those 2 carbons are together. And then we have 4 electrons. 4 hydrogens. Right? Okay. 2, 4, 6, 8, 10. 2 electrons. Where do we put them? Well, there's a good place. But we still have to make an octet for that carbon. So we take these 2, make a double bond out of it. Right? So that one's got a double bond. It doesn't work. How about this one? Let's see. 2 times 4 again is 8. 6 here is 14 electrons. Okay. So do this again. Only now we have 6 hydrogens. Oops. A mistake. Let's see. 2 carbons. 1, 2, 3, 4, 5, 6 hydrogens. Okay. 2, 4, 6, 8, 10, 12, 14. Used them all up. There's your molecule. That one has no pi bonds. So this is our answer. Right. D has no pi bonds in it. All righty. Come to another one. Number 24. Complete the Lewis structure for the, excuse me, for the following molecule. So they've given you part of the structure. It may or may not be complete. All right, so we'll put in what they've got so far. Remember, when carbon is written like that with hydrogens on this side, they're actually attached to that carbon. And that carbon is attached to the next carbon. And this hydrogen is down here, and up here we have another carbon with its hydrogens. CH3 is called a methyl group. Methyl group here, methyl group here. Carbon there, and we have a carbon here, and we have an oxygen there, and then we have another carbon and a nitrogen. Okay? So, let's find out how many valence electrons we have. Right? How many carbons do we have? 1, 2, 3, 4, 5. 5 times 4 is 20. How many hydrogens do we have? 1, 2, 3, 4, 5, 6, 7. 7 times 1 is 7. Okay. And then we have an oxygen, which is 6. And a nitrogen, which is 5. Okay. So we add those together. Let's see, that's 11, 18, 38. I think that's right. Yeah, 38 electrons. Okay, how many have we used so far? 2, 4, 6, 8, 10, 12, 13, 14, 15, 16. Oh, excuse me. Let me try that again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 22, 24, 26. So that means we have 12 electrons left over. I work from our way outside in. Hydrogen can't take anymore, so we're working from oxygen and nitrogen. All right, so let's see. 2, 4, 6, 8, 10, and 12. There we go. So we used up those 12, working our way in. All right. So now we've used up all of our electrons. Okay. This one's got an octet, octet, octet. That one needs an octet. So let's take 2 of these, make a double bond. This one has an octet now. This one needs an octet. It can't get any electrons from this carbon because it doesn't have any to spare. So it has to come from this one, from this nitrogen. So if we take those two and those two, that gives us an octet for this carbon. And it keeps the octet for nitrogen. Okay. So now back to the question. This molecule has how many sigma bonds, how many pi bonds? Right. Every bond is a sigma. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 sigmas. And how many pi's? Well, any place you have a double or triple bond, you've got a pi somewhere. So we got 1 pi here, we got 1 pi there, and 1 pi there. So that's 3 pi bonds. So the answer is 13 and 3, which is E. Okay. 24. And scroll. We'll pick up 26 and 27. Consider the skeletal structure shown below. They're giving us this starting point. Right? Draw the Lewis structure and answer the following. What we have to assume with this structure is that there are no other atoms in this structure. That's it. That's all of them. There are no understood hydrogens. There are no understood whatever. This is it. So we have 4 plus 4 is 8, and we have 5 plus 5 is 10. We have 18 valence electrons that need to be used up. Okay? So we got 2, 4, 6 is 12 electrons. We'll work from the outside in. 2, 4, 6, 8, 10, 12. Okay? This one needs an octet. It only has 2, 4. It needs 6, 8. And this one needs 6, 8. Okay. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18. That uses up 18. Okay? So there's your structure. What's the question? How many pi bonds does the molecule contain? All right? You got a pi here, you got a pi there, you got a pi here, you got a pi here. So it has 4 pi bonds. C is the answer. $27? Yeah, 27. Which of the following molecules contains the shortest carbon-carbon bond? All right, the shortest carbon-carbon bond is going to be the strongest one. Right? So we know that of the carbon-carbon bonds, that's the weakest. Right? The next strongest is this one. The next strongest is that one. And that's as high as we go. Right? So we look at these molecules, A, B, C, D, and E is B and D. E is B and D. Okay, so what's A? C2H2, C2H2, C2H4, and C2H6, and then C2Cl4, C2Cl, yeah, Cl4. Okay, so what do we have here? We've got 2 times 4 is 8 plus 2 is 10. We've got 10 electrons here. Let's do the electrons first. So that's 2 times 4 is 8 plus 4 is 12. And that's 8 plus 6 is 14. And this is 8 plus 4 times, 4 times 7 is 28. So this is 36. Okay. So how about this one? We got a carbon-carbon that uses up, well, let's see, and a hydrogen and a hydrogen. There we go, 2, 4, 6. So minus 6 is 4 electrons. So we have like that. If we take this one and make a double, take this one and make a double, Now we've got 2, 4, 6, 8, 10. Got the right number. So that's our structure for this one. There we go. 2, 4, 6. That's 6 electrons. 2, 4, 6. So how do we do this one? Oops, excuse me. Let's try that again. 4 hydrogens. Nobody said anything, of course. 2, 4, 6, 8, 10. 2 electrons here and here. So we need to move these 2 over, make a double bond. Now we have the same number of electrons, but we have octets for everybody and duets for hydrogens. Okay. Then this one, we have 6 hydrogens. 2, 4, 6, 8, 10, 12, 14. That's it. That's your structure right there. And this one is carbon, carbon, chlorine, 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 2, 4, 6, 8, 10, which is 26, 2, 4, 6, and 12, 14, 16, 18, 20, 22, 24. So we have 2 electrons left over. And we'll put them right here. Chlorine can't hold anymore, so we have to go to the carbon. And we take those 2 and make a double bond. Right? So this is D, this is B. Now, of course, the shortest bond in here is going to be the triple bond right there. Right? So the answer is A. But just suppose that we had something else up here, right? Another single bond, for instance, somehow. Then we would look at B and D and compare those, because now the double bonds are the most that we have for each of these carbons. Double bond here and double bond here. All right. Are they equivalent? Are those carbon-carbon bonds equivalent? Well, theoretically, yes, except for the effect that chlorine has on the molecule. Chlorine is a very electronegative atom. It's going to pull electron density away from that bond. It's going to pull it this way, and that weakens the bond. So this would be the stronger of the 2 right here. Right, but fortunately, that's not the question. we don't have to break a tie. Right? This triple bond is the strongest, and that answers the question. All right, 28. All right, when comparing Be2 and H2. Okay. I think what we're supposed to do is decide which of these Roman numeral 1, 2, 3, or 4 are valid. Right. So let's say Be2 is more stable because it contains both bonding and anti-bonding valence electrons. All right. What would be the molecular orbital structure for this one? Well, we know it's going to be like that and like that. And this only has 2, right? So that's it. Right? We don't even have that. So its bond order is going to be 1. Right? 2 divided by 1. 2 divided by 2, excuse me. Beryllium, on the other hand, is, let's see, sigma 1s, sigma star 1s, sigma 2s, and sigma 2s star. And if we need any more, we'll put them in. But beryllium has, let's see, a total of 8 electrons. If we're only considering the valence shell, then we can throw these out. And in that case, beryllium only has 4 valence electrons. So we put 2 in here and 2 in here. Correct? Okay, that gives you 4. This bond order is 0. That molecule is very unlikely to even exist. Beryllium is more stable because it contains, well, first of all, it's not more stable because its bond order is 0. So 1 cannot be it. Right? 1 is false. How about 2? H2 has a higher bond order than Be2. Yes, it does. So that's true. How about 3? H2 is more stable because it only contains sigma 1s electrons. Yeah. Yeah. Okay. How about 4? H2 is more stable because it is diamagnetic, whereas Be2 is paramagnetic. Well, no, they both have paired electrons. That's paired, that's paired, that's paired. Right. So they're both, let's see. Scratch my head for a minute. Paramagnetic is drawn into the field. Diamagnetic is repelled by the field. So they're actually diamagnetic, both of them, if they even existed. And this one is unlikely to exist anyhow. Right? So 4 can't be true. Right? So 2 and 3 are the only ones that are true statements. And that would be C. All right, 29. Okay, which of the following species is paramagnetic? Okay, so what we need to be paramagnetic is at least 1 unpaired electron. So A, B, C, and D, and E, none of these. Okay, so we have C2O2, F2, C2O2, F2, and Li2. All right. So C2, if we're only going to, we really only need to be interested in the valence shells. So C2 is working from the second period. So we can leave the first period out. So the second period would be sigma, let's see. We're going to have SP mixing here. C2 is SP mixed. O2 is not mixed. F2 is not mixed. Li2 is mixed. All right, so that means this 2s and sigma 2s star. In fact, if you go to the end of the review document, and it'll be on the exam too. If you go to the end, you'll see that mixing chart. Where is it? Keep going, keep going, keep going. Wait a minute. Where'd it go? There it is. Okay. This one might be a little easier to read. Will it? No, we need this one. Okay, so lithium, this one, and carbon are going to have SP mixing. So what that does is, if we look at the order, we find that, let's see. I got these things in my way. I'm going to scoot them over just a little bit. There we go. What we find is sigma 2s star, sigma 2p for oxygen, and then oh, carbon, I'm sorry. Carbon. Carbon is bonding, anti-bonding, sigma bond. Sigma 2p bonding and pi 2p bonding. And then wait a minute. No, sorry, I got that backwards. This is pi, this is sigma. There we go. And then from then on, it's consistent. These two are the ones that are swapped for SP mixing. There we go. Okay, for oxygen and fluorine, these two are going to be the same. These are going to be in this order: 2p, pi 2p, then pi star 2p, and then sigma star 2p. So the same for this one: 2p, pi 2p, anti-bonding 2p, and sigma star 2p. There we go. Now lithium is going to be mixed. And lithium is in the second period. So it's going to be like carbon. It's going to have sigma, sigma star. It's going to have pi 2p, sigma 2p. Then it goes back to pi star 2p and sigma star 2p. All right, so now we have the energy order of the molecular orbitals for each one of these. Now we can fill them in. All we need is the valence electrons because we're not using the 1s orbitals. Okay, so this would be 8, this would be 12, this would be 14 valence electrons, and lithium would be lithium. Lithium is 2, right? Because lithium is way over on the left-hand side in the alkaline metals. Each lithium only has 1 valence electron, so it only has 2 electrons. And these are valence electrons. Okay, now we can fill them in. Right, 8. We have 2, 4, plus 4 is 8. Right? We don't need the rest of it. And if this has got 4 in it, it's going to be 1, 2, 3, 4. Those are all paired. That's diamagnetic. It is repelled from a strong magnetic field. Okay. This one is 12. 2, 4. 4 is 8. And then we need 4 more. Right? Yeah, 4 more. That means this one is diamagnetic. Correct? Oxygen. Okay, I did something wrong. 2, 4. Oh. Duh. Okay. I knew something had to be wrong because I know oxygen is paramagnetic. So I put too many electrons in that one. There's 2 in that. So that's 6. We need 6 more. Right? So in this one, we have 4, and we get 2 in this one. 1 here and 1 here. That's paramagnetic. Okay. Fluorine. Okay. 2, 4, 6. Means 8 more. So 4 and 4 is 8. Right? That's diamagnetic. This one's diamagnetic. How about lithium? Well, it's only got 2 electrons. They go right there. Okay. So this one is diamagnetic. The only paramagnetic is oxygen. Now, is that the question? 29. Let me go back up to 29. And 29. Here we go. Paramagnetic B is oxygen. Oxygen is the only one that has unpaired electrons. That makes it paramagnetic. All right, 30. Which of the following species is paramagnetic? Wait a minute. Oh, I'm reading the wrong one. 30. For how many of the following does the bond order decrease if you add 1 electron to the neutral molecule? All right. So we got B, C, P, and F. Okay. Oops, that's not the way it goes. E, C, P, F. And that's it. Okay, then A through E. Zero, 1, 2, 3, and 4, correct? Yeah. Okay. How many of these does the bond order decrease if you add an electron? So we're going to add an electron to each one. Well, in order to do that, we need to know what the neutral configuration is. Right. All right, B2. Let's go back to our diagram. Be less likely to make a mistake. And there we go, B2. So that's sigma, sigma star, and pi. Sigma, sigma star, and pi. And we have 2, 4, 6. Boron, yeah, boron has 3 each, so there's 6 electrons, 2, 4, and 2. So we have it like that. Okay. How about carbon? Right? Carbon is sigma, let's see, this is B2, this is C2. Carbon has 8 electrons. So it has 2, 4, and 4 is 8. Okay, so this one has like that. Phosphorus. Okay, phosphorus is in the nitrogen family. So what we would do is we would take the nitrogen arrangement, only this time phosphorus is composed, the valence molecular orbitals are composed of 3s and 3p, but we use the same arrangement. So it'd be the same as nitrogen, only instead it would be 3s. And let's see, we're going to need another sigma with 3p, right? Okay. So phosphorus has how many valence electrons? Well, it has 10, 5 each, 10 electrons. So 2, 4, 8, and 2 more here. So that means, oops, like that. 2, 4, 8, 10. And the last one is fluorine. Okay, fluorine has 14. So with fluorine, let's see, we need to go up, let's see, we're in the 2 S's here. Sigma 2s, sigma star 2s. Then we go to pi 2p. We go to sigma 2p. We go to oops, a mistake. We do sigma 2p. Then pi 2p. Then pi star 2p, and then sigma star 2p. No mixing here. Okay, so 14 is 2, 4, 2 more, 6, and then 4, and then 4 more here. So that should be 8, 10, 14. Okay, so we don't need this last one. Oh, we're going to add an electron, so I better put it back. Sigma star 2. Okay. Let's go back up to 30. There it is, right there. Okay. For how many of the following does the bond order decrease? Bond order, remember, is the number of bonding minus the number of anti-bonding divided by 2. So if we either subtract bonding or add anti-bonding, we get a decrease in bond order. So in this case, we're adding an electron. So the one where the bond order is going to decrease is the one where we add electrons to the anti-bonding orbitals. So if we add an electron here, it goes in there, right? That's an increase in bond order. If we add one here, oh, carbon. Let's see, carbon is going to be sp mixing. So let's see, we got this one, this one. Yeah, and then this one. Right there. So we're going to add one to that one. That's a bonding orbital. That increases its bond order. So we haven't decreased one yet. Right? This is increase bond order. How about this one? Well, we're going to add one here. That's bonding. That's increase. How about here? This one will add one there. So that will decrease the bond order. So only one decreases the bond order. That will be B here. Okay? Only one of them adds that electron to an anti-bonding orbital. All right, 32. Order the following from the shortest to the longest bond. Let's see. What's that? Don't forget the effect of atomic radius and orbital size. Okay. All right, we've got, I'm going to put it over here. 32. I guess we skipped 31, didn't we? Yeah, skip 31. Okay, C2, B2, H2, and N here. C2, B2, H2, N2. I think we can answer this one. All right. We have to assume that these are all single bonds. Right? Because, well, hold on a second. We could have C2 All right, let's approach this from molecular orbital. Right. C2 molecular orbital. Here we go. So what's the bond order for this one? We got 2 minus 2, and then don't need that one because it's C2. All right, so we have 4, 6 minus 2 is 4. 4 divided by 2 equals 2. So C2 has a bond order of 2. B2 has a bond order of 2 plus 2 is 4. Excuse me. No. That's right there. 2, 4, 6. 4 minus 2. 4 minus 2 over 2 is 1. This is a bond order of 1. Hydrogen is 1 also. We did that one at the beginning of the chapter. And N2 is a bond order. Remember, we calculated that one at 3. Right? It's a triple bond. All right. So if we put them in order of shortest to longest, shortest would be the strongest. Right? This would be the shortest. Be N2. Shortest, longest. Okay. So this was the shortest. The next one would be C2. And then we need to have, we got a tiebreaker between B2 and H2. Which one would be the shortest? Well, boron is making its single bond from the second period, 2s and 2p's, right? So it's further out when those orbitals interact. The core doesn't interact, right? So it occupies this space, and now we're out here. So the boron atoms are farther apart, right? So that weakens the bond. So the weakest bond would actually be this one, B2, right? It would be the longest bond, and then H2 would be here. So N, C, H, and B. N, C. Wait a minute. Why is H there? Oh. Okay. I should have continued with that logic, right? Why? Because this one is based upon sigma 1s, right? Those nuclei really get close to make this bond. This triple bond is with p orbitals, p orbitals, p orbitals. Well, s's and p's. So that puts the nuclei of hydrogen closer together. Didn't say anything about the strength of the bond. It says the length of the bond, shortest to longest bond. Now that may seem like it's running counter. It's counterintuitive. If you go back to the statement that we made earlier, that a double bond is stronger and shorter than a triple bond, than a single bond, and a triple is shorter and stronger than a double. That's only if you've got the same atoms in that progression. Now we've gone down to a hydrogen, which puts those protons, it's just 1 proton each. I mean, they're very close together. Right? So the shortest bond may not be the strongest, but the shortest bond is hydrogen. So it needs to be over here. That's why the answer is A. N2, C2, B2, that's correct order. H2 needs to come first. It is, in fact, the shortest bond. (34) Let's see, am I going to need these anymore? Yeah, I might. O2 plus 34. What's the question? Which of the following has a bond order of 1.5? We're looking for bond order 1.5. Okay. There's no oxygen in there. Okay. So oxygen is going to use the fluorine molecular orbital Right? So let's see, F2 doesn't have that one in it. All right, so this is 12. Well, so we have 2, 4, 6, and 4 is 10, and then 2 more here. Okay. O2 plus means we subtract an electron. So O2 plus means this is only 1. So what's the bond order of this one? Well, let's see, 2, 4, 8 minus 2, 3 divided by 2. 5 divided by 2 is 2.5, isn't it? No. Wait a minute. Let's see. 2, 4, 8. 8, that's right. 2, 3. Yeah, that's right. That's right. 5 divided by 2 equals 2.5. Right. So O2 is not it. Right. How about N2? Well, we know the bond order of N2. It's a triple bond. Right. So N2, let's see, A, B, C, D. O2 plus N2. This is 2.5. This is 3. C is C2. C2. Here's C2. That's yeah, 2 times 8. 2 times 4 is 8. 2, 4. So this one would be 6 minus 2. 6. All right, 4 plus 2 is 6. Minus 2 divided by 2. So that's 2 and 4, that's equal to 2. Right. And the last one is C2. No? Oh, I skipped O2 minus. C2, 2. O2 minus. Okay, if we add an electron to this one, right, it would have been here. Then we add another one, which would be 3. That means 2, 4, 8 minus 2, 5. Well, that's 3 divided by 2 is 1.5. So E is, no, excuse me. This one is 1.5. And E is probably none of these. Yeah, E is none of these. All right, so that one's not it. That one's not it. That one's not it. O2 minus is 1.5. So it actually weakens the bond when you add an electron, because that electron went into a non-bonding, an anti-bonding orbital. All right. 36. Which of the following statements about the molecule Bn is false? Assume sp mixing. All right. This molecule with sp mixing. Right? So sp mixing means that it's going to be like this one. Yeah. Bn, sp mixing. Let me go down. Let's go down to our table. There we go. Bn. That makes sense. Boron here and nitrogen both have sp mixing when they're homoatomic, diatomic, homoatomic molecules. So when you put those two together, it makes sense that there's sp mixing. Okay, so in that case, what we're going to be working with is, let's see, I hesitate to erase that. for this molecule, we're going to have a configuration in the valence shells part of the molecular orbitals as sigma 2s, sigma star 2s. Let's see, sigma star 2s, then pi 2p and sigma 2p. Pi 2p, sigma 2p. Yeah. Then pi star 2p and sigma star 2p. Let's see if that's enough. Boron has 3, nitrogen has 5, so we have 8 electrons. 2, 4, and 4 is 8. That's it. That's all we need. All right, now we'll go back. What was the question? 36. Let's go back up. Let's see. Here we go. Which of the following statements about the molecule is true? Okay. A says it's paramagnetic. Is it paramagnetic? No. It has, right? They're all paired, right? So it's diamagnetic. Right? So A is false. How about B? Its bond order is 2. All right. So let's see. 4 plus 2 is 6, minus 2 is 4, divided by 2. Yes. Bond order 2. That's correct. C, the total number of electrons is 12. No, the total number of electrons is 8. Oh, wait a minute. The total number of electrons. Right. We only counted 8 of them. But we have boron actually has 5 electrons total. Nitrogen has 7 electrons total. That's 12. 12 electrons total. Trick question. That one is true. Just because we didn't count them doesn't mean they're not there. It has 2 pi bonds. All right. How do we tell pi bonds? We look at the pi molecular orbital. Right. It has 1 pi bond here, 1 pi bond there. 2 pi bonds. Correct. Oh, we're looking for the false one. Right? True, 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 false. A is false. There you go. They're not all true. A is the false one. All right. $38. Ooh, we're into our lab time now. Which of the following molecules or ions is not paramagnetic in its ground state? Not paramagnetic. Okay. O2, let's see, 12, 2, 4, 6, 10. 12. So let's see. A is O2. A is O2. O2 is paramagnetic because it has 2 of these orbitals, 1 there, 1 there. They're unpaired. That means it's paramagnetic. So this one is paramagnetic. How about O2 plus? O2 plus. Well, O2 plus means we take 1 electron away. So we go to the top, take 1 of these away. It's still got an unpaired electron. So this one's paramagnetic. B2. B2, here it is, B2. All right. This one is paramagnetic, right? Let's see. Boron, yeah, 3, 6, 2, 4, 6. That's correct. That's paramagnetic. And NO, no SP mixing. NO. All right, so NO would be with no mixing, would have O2's layout. We have 5 valence here, 6 there, so that's 11. So we have sigma 2s, sigma star 2s, and sigma 2p, and pi 2p. All right. Let's see. We may need a star 2p. Let's see if we do 11. So it's 2, 4, 6, 10, and 1 is 11. This one's paramagnetic, right? That one right there is unpaired. And how about E? E, F2. F2. Let's see, we have F, yeah, we got F2 right here. So 14, 2, 4, 6, 10, 14. Okay. These are all paired, right? They got that, like that, like that. Okay, so those are all paired. This is diamagnetic. So E is the one that's not paramagnetic in its ground state. $39. All right. In the molecular orbital description of CO, assume SP mixing. The highest energy electron occupying anti-bonding orbital 6, there's 2 unpaired. All right, so what we need here is the molecular orbital structure of CO. CO with SP mixing. All right. SP mixing is going to be characteristic of nitrogen, carbon. So we'll go with carbon. Yeah, we'll go with carbon for our arrangement here. So we got 2p, got sigma star, 2p, we got pi, 2p, we got sigma. Oh, excuse me. No, this is S. S, 2p, 2p. Then we do pi star, 2p, and sigma star, 2p. There we go. Okay, this has 4 valence electrons. This has 6, so that's 10 electrons. 2, 4, 4 is 8, and then 2 more. All right, so what's the question? The highest energy electrons occupy anti-bonding orbitals. No, that's bonding orbitals, right? So A is false. 6 molecular orbitals contain electrons. 1, 2, 3, 4, 5. That's false. 5 MOs, right? Remember, this one has 2 in it. These each have 1. And so that's 1, 2, 3, 4, 5. C, there are 2 unpaired electrons. No, there are not. They're all paired. They're all paired. How about D? The bond order is 3. Well, let's calculate it. What's the bond order? That's 2 plus 4 is 6, 7, 8. 8 minus 2 divided by 2, right? Minus 2. So that's 6 divided by 2 equals 3. That's your winner right there. D is correct. All right. 41. Which of the following statements about CO3 2- ion is false? Orbitals, sp2 hybridized ion is expected to be diamagnetic. Okay, so we need to use both approaches to answer these questions, both the valence bond theory and the molecular orbital theory. So for the first one, A, the orbitals on the carbon atom are sp2 hybridized. Is that true? sp2 carbon. Right? CO3 2-. CO3 2-. All right. So carbon has 4 valence, 6 for each one of these. 3 times 6 is 18, and then 2 more. Right? So that's 24. All right, so we have carbon, we have 3 oxygens, right? 2, 4, 6. That's 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right. So carbon needs a double bond here. So that's one possible Lewis structure, right? It would resonate with this one, move the double bond here, move the double bond here. So you have 3 possibilities there that resonate with the valence bond theory. All right. So the orbitals on the carbon atom are sp2 hybridized. 1, 2, 3. sp2. That's correct. Right? That's true. We're looking for the false one. Right? So A is true. B, the ion is expected to be diamagnetic. All right, so this is A, B. Now we need the molecular orbital for CO3 2-. All right, carbon C2 has sp mixing. O2 does not have sp mixing. So I would say that there's no mixing here simply because you've got 3 oxygens and only 1 carbon. Right? So let's approach it that way and just see what answer we get. All right, if there's no sp mixing, we're going to use the oxygen format here. 2 to S sigma star 2s. See, I don't need that yet. Sigma 2p pi 2p pi star 2p and sigma star 2p. I don't know if that's enough. We have how many valence electrons? 24. Right? 2, 4, 6, 10, right? 14, 16. Right, so that's 16 minus 16 is 8. I need room for 8 more. So what's past 2p? The sigma 2, sigma star 2p. Let's go to the bottom and look. Sigma star 2p. All right, we're going to have to make it up on our own. We would have to go to S. 3s and 3s star. All right, so we've got 2, 4, 6, 10, 14, 16. 18, 20. So that means we have 4 more we need. So what comes after this one? Right, we have sigma 3p. And that'll be 2, 4, 6, 8, 10, 12, 14, 18, 22, 2 more. So what comes past this one? The next one up will be pi 3p. And we got 2 more electrons, so 2. That means these are unpaired. All right, so let's go back up and look at 41. Can't see what I'm doing. There we go. The ion is expected to be diamagnetic. Diamagnetic. That says it's paramagnetic. Did I count right? 24 electrons. 2, 4, 6, 10, 14, 16, 18, 20, 22, 24. So according to that, this is paramagnetic. All right. All right, so I must have these, somehow I've got these out of order. Right. 2p. Let's see, 2p, 2p. We have how many orbitals going in for oxygen? We have a 2s and 2p's. 2s, 2p. 2s, 2p, 2s, 2p. This is 3 of them. So that's 4, 12. And then carbon is 2s, 2p2. So 1, 2, 3, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The only thing I can figure is that these two are reversed. There must be mixing. In other words, if we put this one up here and this one down here, and we got 1, 2, 3, 4. Now, if this one's up here, we got all 4 of them in there like that, like that. So that says that there's mixing at this level. That's the only thing I can figure that would make it diamagnetic. The CO bonds are different lengths. Well, we know the CO bonds are the same length. Right, because they resonate. And when we measure them, they are exactly the same length. So this one is true. This one we have to assume is true. How about D? D, the ion has a total of 24 electrons. Oh, CO bonds are different lengths. Right? Different lengths. Right, so that one's false. C is the false one. Right. D, they do have 24 electrons. Okay. That was a toughie. Let's go to 42. How many electrons are involved in pi bonding in benzene? How many electrons? Okay. We drew the benzene ring earlier, right? It was like this, like that, like that. Or another way around. So how many electrons are involved in pi bonding? Well, this is a pi bond. This is a pi. This is a pi. 2, 4, 6. 6 electrons are involved in pi bonding. All right. 45. Which of the following has the highest bond dissociation energy? The bond dissociation energy, which one has the strongest bond? So if we say N2, we start with N2, and the rest of them are going to be ions of N2. All right. So if we get the N2, then we can add electrons or take away electrons from its molecular orbital structure. So N2 is going to show mixing. So which ones these were mixing? Boron, carbon, phosphorus. Yeah, carbon showed mixing. So we have sigma 2s, sigma star 2s. We have sigma 2p, and no, we have pi 2p mixing. We have pi 2p and sigma 2p. Then we have pi star 2p and sigma star 2p. Okay, so now we have valence electrons for nitrogen would be 2 times 5 is 10. 10 electrons. 2, 4, 8, and 2. Okay, let's see if that's right. 2 plus 2 is 4, 8. 8 minus 2 is 6, divided by 2 is 3. Okay, so this bond order is 3. Okay, how about B? N2 minus. N2 minus. Where's the extra electron going? The extra electron going into an anti-bonding orbital. Right, so now that's 2.5 bond order. The C, N2 2 minus, N2 2 minus. Put another electron into the anti-bonding. That brings it back down to 2. You can calculate the bond orders and you'll see I'm right. N2 plus, N2 plus. Okay, so we're subtracting an electron now from this one. We subtract it from a bonding orbital, which reduces again to 2.5 from 3. 3 to 2.5. Why? Because we're removing a bonding electron. Right? Remove 1, divide by 2 is a half. So we bring it down by a half, 2.5. And then E is N2 2 plus. N2 2 plus. We remove 2 electrons from a bonding orbital. That brings it down a whole. So now it's 2. So this one has the strongest, shortest bond of that group, the highest bond dissociation energy. How much energy does it take to break the bond? The strongest one, the one that requires the most energy, is that triple bond. The bond order 3. This is a bond order of 2.5, 2, 2.5, 2. All right, 47. Which of the following molecules or ions does not contain a central atom with D2sp3 hybridization? So we're looking for the one that's not D2sp3. All right, 6 groups around the central atom. First one, xenon pentafluoride plus. Xenon pentafluoride plus. Okay, so we have 8 electrons here. 5 times 7 is 35. Minus 1 because it's a plus charge. Right? So 34 and 8 is 42. Okay. Xenon 1, 2, 3, 4, 5. Okay, 2, 4, 6, 8, 10. 32. 2, 4, 6. 6 times 5 is 30. Right? 2. So that means 2 has to go here. And that's a plus. Okay, so this one has 1, 2, 3, 4, 5, 6 groups. That's D2sp3 hybridization. Okay. So this one is D2sp3. How about B? B, IF4 minus. IF4 minus. Okay. 4 plus 1 is 5 times 7 is 35 plus 1 is 36. Okay. So I in the middle. 1, 2, 3, 4. F, 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 F. That's 2, 4, 6, 8, which is 28. 2, 4, 6. 6 times 4 is 32. Oops. I did something wrong. Hold on a second. 5 times 7 is 35 plus 1. 36 is right. Okay. So 2, 4, 6, 8 minus 8. Did I calculate? Yeah, 28. 2, 4, 6, 8, 10, 12. Oh, there we go. 4 electrons left over. They have to go here and here. So 1, 2, 3, 4, 5, 6. This was D2sp3 hybridization. How about C? SF6. SF6. Okay, sulfur is 6 electrons and 6 times 7 is 42. So we get 48. Sulfur 1, 2, 3. Let's see. 1, 2, 3, 4, 5, 6. Okay, 2, 4, 6, 8, 10, 12. Equals 36, 2, 4, 6. 6 times 6 is 36. All right, that's it. All right, that's D2sp3 hybridization. We got 6 groups around that one. That one's D2sp3. How about D? SEF5 minus. SEF5 minus. Okay, selenium is like oxygen has 6. 5 times 7 is 35 plus 1. All right, so 36 is 42. So we have selenium and we have 1, 2, 3, 4, 5 fluorines. 2, 4, 6, 2, 4, 6, 8, 10. Right, that's 32. So 6 around each one of these is 30. We have 2 left over, goes here. So we have 1, 2, 3, 4, 5, 6. That's D2sp3. Right. All right, so they're all D2sp3. That's why E is the answer. All right, we skip over a few and we come down to here we go. All right, so we're back to the valence bond theory for this one, I do believe. Yeah. Let me see if I'm going to need those. Let me go down and see if I'm going to need those molecular orbitals. O2 and N2. Okay. Okay, that's good. So let's fill out this table. You only got 2 more to go. This is number 60. All right. In this table, we've got the only thing we're given is the top header and the left column plus the sp3. So we've got 3 molecules, A, B, and C. A, B, C. And then down the left-hand side, we have electronic geometry. We have hybridization. We have bond angle. And we have an example. Okay. So we mark it off. Get weak. Let's try this. Yeah. Okay, and we're given the sp3 hybridization for this one. sp3. Okay, the text tells us how to fill in the rest. A, B, C. Molecule A has a hybridization of sp3, okay. Molecule B has 2 more effective pairs around the central atom than molecule A. So if this has 2 more, we've already used up 1s and 3p, so we have to go to, let's see. Use a different color. About blue. We have to go to D2sp3. Okay. Next, molecule C consists of 1 sigma bond and 2 pi bonds. Molecule C consists of 1 sigma and 2 pi's. Now, how can that be? All right. If you can have 1 sigma bond and 2 pi bonds, how do you get those other 2 pi bonds? You can only have 1 sigma bond, right? That's it. That's all we're given. So the only way you can get the other 2 pi bonds is to make a triple bond. Because if you add something else over here, it's another sigma, and we can't do that because it can only have 1 sigma bond. So XY is a triple bonded molecule, which means you know, that's wrong. It's not D2sp3. That is wrong. It's SP hybridization. Right? SP hybridization. Right. All right. So what else can we say about this? Well, sp3 has to be tetrahedral. D2sp3, 6 groups, has to be octahedral. SP has to be linear. Okay. So the bond angle here can only be 180 degrees. Okay. This bond angle is 109.5. How about octahedral? Well, I have to draw a picture. So we have something in the middle, and then we have like that, like that. What do we have? Well, we have 90 degrees here, here, and here, 90 degrees there. We have 90 degrees. If we have a bond there, that's 90 degrees. And if we have something occupying these positions, That's 180 degrees. So the most you can have is a 90 and a 180 degree. That's the maximum. Okay. What's a good example for sp3 hybridization? Well, that's dumb. What's the example? The example would be something like, I don't know, methane or carbon tetrachloride, right? Oops. That's not an example. An example would be something like, methane would be a good example of a sp3 hybridized molecule. Octahedral. Let's see, we need 6. How about sulfur hexafluoride? About that one. And let's see, a triple bonded molecule. We could do this one, or we could do that one. Those are both triple bonded. Okay, so that's 60. And I got to correct this. I got to fix that. See, I can save it. The linear is already corrected, but I need to get access to the editor to fix this one. Let me try one other thing. CH4. Okay. That 4 is in the wrong place, but I'm going to save it anyway as a reminder. All right. Last one. I need a red marker. Last one, 61. All right, draw a molecular orbital diagram for O2 and N2 using molecular orbital theory. Explain why the removal of one electron in oxygen strengthens the bond, while the removal of one electron in nitrogen weakens the bond. We've already done the nitrogen, right? We know what happens to the nitrogen. So if we're going to draw a full energy diagram for nitrogen, we need sp mixing, right? So if we do nitrogen, right, we've got an energy diagram here. Right? And we've got 2 nitrogens. And we're only going to use the valence bonds. So that's 2s and 2p. Right, so we've got a 2s here. Let's see, right there, there. And we've got a 2p up here. 1, 2, 3. 1, 2, 3. Okay, so this one is going to give us a sigma from the 2s star here and a sigma from the 2s bonding orbital there. This one's going to give us, since there's mixing, we get the pi, we get 2 pi's down here, and we get a sigma bonding up here. So this pi bonding from the 2p, and this pi bonding from the 2p, and this sigma bonding from the 2p. Then we get the antibond. All right, so this is going to be pi antibonding from the 2p, pi anti-bonding for the 2p and sigma anti-bonding for the 2p. Okay. So let's see if we got enough. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. Now we started off with 5 valence electrons each. Here, here, 2, 3, 4, 5. There. So now we're going to go into use the Aufbau principle, lowest energy first, and Hund's rule. Right? So that's 2, 5, that's 10 electrons. So 2, 4, 5, 6, 7, 8, 9, 10. Okay. Now we do oxygen. Oxygen starts off with 2s here, and it has 2 p's here and here, and each oxygen comes with 6 electrons, so we have 12 total electrons. And 1, 2, 2, 3, 4, 5, 6. 1, 2. There we go. Okay. Now, when this one forms molecular orbitals, these two are just like the nitrogen, right? A sigma 2s and a sigma star 2s. But this one goes straight to the sigma 2p. This one goes to the pi 2p. And then we go to the pi antibonding from the 2p, and then sigma antibonding from the 2p. Okay. All right. Let's see. That's not. Let's be consistent here. This one's 2p pi. There we go. So we've got 12 electrons. We're going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Now that we've drawn those, the question becomes, how do we explain when we remove 1 electron from oxygen, strengthens the bond, remove 1 from nitrogen, weakens the bond? Right. For this one, we're going to remove 1 electron. And when we remove 1 electron from this side, the bond order goes up. And when we remove electron from this side, the bond order goes down. The reason is that for dinitrogen, we're removing a bonding electron that weakens the bond. Right? It reduces the bond order. Whereas if we remove 1 from oxygen, dioxygen, we remove an anti-bonding orbital, an anti-bonding electron, which increases the bond order, right? Because it's bonding minus anti-bonding. If you subtract fewer, right? You subtract fewer anti-bonding electrons and divide by 2, you get an increase in the bond order. That's the explanation. All right. You just put it in your own words. Well, there it is. Okay, that's it for our review. And we'll come back Thursday for the exam on this chapter. And then next week, we'll spend the whole week reviewing for the final. All right, so we've got plenty of time to review. If you're here and I haven't checked your lab notebook, the final check on your lab notebook, then you can bring it with you. Otherwise, you're gonna have to take pictures of all the pages that you've done and turn them in on Brightspace. I'd rather check them in person. It'd be quicker that way, but you have that option.